Okay, so let's look at the nth roots of a complex number. We're going to start with the example of z cubed equaling 1, wherein z could be defined as a plus ib. So values along the real axes would be the a, values along the imaginary axes would be the b or ib, and they would come together to give you a point, for example, in these quadrants, in these four quadrants. And we will discuss this further in a moment. And if you haven't gone through that idea, I would suggest you go through past videos or have a look up just generally how to depict complex numbers. You can write it in the form x plus iy, which is how we're going to go forward, which is the same to represent the real along the x and the imaginary along the y. Seeing as z has been defined as z cubed equals 3, or sorry, that this has been defined as z cubed equals 3, then we can do some rearranging to say that z is equal to 1 to the power 1/3, and therefore z is equal to 1. Now, z being x plus iy, we can substitute, or we can rewrite this z as x plus iy cubed equals 3, and we're left with this x plus iy cubed is equal to 1. No, it's not 3, sorry, it's equal to 1. And there is no imaginary, it's just that it's equal to 1. That is to say that the plus I is being multiplied by 0 here is another way to view that. And we are left with a vector-esque line on our real axes of value 1, considering that z is equal to 1 as depicted here. Going forward, what does this mean? How can we utilize this to better understand the concept of the nth roots of a complex number? Let's go recap again. I started off with z cubed equals 1. We did some rearranging and said that therefore z, which is x plus iy, is equal to 1. Since it's equal to 1, x plus iy being this part here, and this up here, if it's equal to 1, there is no imaginary because there is no imaginary part, there is no b, there is no y, it is 0, hence it is just a value along here. Thus we need to represent the number 1 as a complex number better than just this 1 plus 0i, or for example just 1. And we can do this considering the following information. That is to say that we are aware that when you have a complex number, z, as we've described as x plus iy, we can utilize trigonometry to state it. So for example, to do this, it's worth recalling that z is also r cos theta plus I sin theta, because your x cos theta being adjacent to my hypotenuse is also x over r. So r cos theta is x, which is where this part comes from. Instead of x here, we've got r cos theta. And the I sin theta, the sine theta there is replacing the y for the rate as a result of sine theta being opposite divided by hypotenuse, and in this triangle, for example, opposite divided by hypotenuse. And so r, which is our hypotenuse, that length here is r. Then we have r sine theta equals y, and we substitute that y in to produce z equals r cos theta plus I sine theta. This is advantageous. It is better than as we've described our x plus iy for z, for various reasons that we will come to in a moment.